hendesehaneydi ilk adım. Aynı zamanda Osmanlı İmparatorluğu'nun bilime, tekniğe, mühendisliğe attığı ilk adımdım. Yıllar içinde adım ve binalarım hep değişti ama yönüm, vizyonum hiç değişmedi. Sınır tanımayan mühendisler yetiştirdim kurulduğum günden beri. Talebelerim gemi mühendisliğinden harita mühendisliğine her alanda yeteneklerimizi ülkemizin hizmetine sunarken ben bünyeme yeni bölümler, teknikler kattım. Osmanlı İmparatorluğu'nda, askeri teknolojide de, bina ve yol imarında da, Hicaz'a uzanan demir yollarının arkasında da yetiştirdiğim mühendislerin tekniği, çalışkanlığı, vizyonu ve emeği vardı. Kurulduğum ilk yıllarda da hayallerim hep yerden göğe kadardı. Mizah zekanın zekatıdır dedim. Şaka dergisinde espriye, karikatüre, bilim ve teknik kattım. Öğrencilerim 1909-1928 yılları arasında mizahın mühendisçesini yazarken dünyaya o günlerde de başka baktım. Söz uçar, yazı kalır sözünü kendime şiar edindim. Kurulduğum günden beri yayın faaliyetlerine ayrı bir önem verdim. Ülkemizin faaliyeti bugüne kadar devam eden ilk matbaası ve ilk yayın evine ev sahipliği yaptım. Ülkenin en eski teknik eserine de, bugün bir eser üretmek isteyen öğrencime de mürekkebin ilk damlasını ben verdim. Genç Cumhuriyet'in inşası ve kalkınmasında teknik tüm ihtiyaçlar için yük mühendislerin omzundaydı. Mühendisleri yetiştirme yükü Türkiye'nin ilk teknik üniversitesi olarak benim omzumdaydı. Bir yük gibi değil, bir ödül gibi sırtlandım ülkemin geleceğini. Mirasımdaki birikimi bir milletin heyecanı ve umuduyla birleştirdim. Cumhuriyete umut olan binlerce genç yetiştirdim. Akademisyenlerim ve yetiştirdiğim binlerce öğrenci Türkiye'nin ilklerine ve unutulmazlarına imza attı. Kapımdan giren herkes bana güzel sözler bıraktı. Sadece Türkiye'de değil, mezun olan öğrencilerim dünyanın başka ülkelerinde.
Okay. Good morning to everybody. I will talk today of a unitary outlook on the concept of stability or instability, who knows. And this time I don't have a PowerPoint presentation. I will try to present ideas and some graphs and some simple drawings without having a presentation with me. So if you don't mind, I will sit down in front of my computer and I will use it as it were a whiteboard. My presentation is based on my past and my maybe also my future. And since I was taught about elastic stability or instability by my professor and teacher on strength of materials back in 1989, and I did my master thesis on stability. My first investigations and papers are also about stability. Well, not actually all, but and I have always been fascinated by this subject. There will be nothing new in what I say, but as far as I know, my background is one of the, it is not because it's mine. The shoulders I rely on are maybe the most comprehensive. I dare to say maybe internationally throughout the world, because I rely on this, on the shoulders of these guys. For instance, Warner Czerzus-Keuter, who taught to my academic grandfather, who on its turn taught to or worked with Angelo Luongo. Angelo Luongo is worldwide known as one of the best experts in stability or instability, and I will more or less follow his last book, which is for the time being written only in Italian, so I will not give you the reference. He is preparing the English version of it together with his working group, but maybe who's interested in the basics can rely on this one, which is maybe still, after all these years, one of stability of structures, Elsevier. (1994) maybe. Let me just check. '90. It is an old book compared with nowadays standards, but it still presents all the necessary concepts. Okay, why did I write instability or stability? It's just like, what is the difference between linear and non-linear? Do we deal with real or virtual? Well, do we study stability of structures or do we study instability of structures? Well, actually, one should not talk about stability, because stability is something, for instance, relying, well, not for instance. Stability is a concept relying on a single sample, a single phenomenon. So that pendulum with length L and mass M is stable or not stable. The motion, so the single phenomenon related to the single sample, can be stable or unstable with respect to something. Sorry. When we deal with a family of samples, so with a class of phenomena, it would be better to talk of this thing here. That is bifurcation, which the word suggests the fact. The word suggests the fact. Bifurcation is when you run through a path, you have a qualitative change of the path. You can either go left or right. You have to make a choice. A bifurcation is something relying something related to a class or to a family of samples, and it is characterized by a qualitative change of the behavior. There are mathematical, rigorous mathematical descriptions, but just to make things simple and maybe intuitive, just imagine that instead of the projector there's a telescreen catching or a camera catching high-speed photographs of this room. And take, for instance, 10,000 photos, 10,000 shots. Well, of course, if you run through all these 10,000 shots, of course, by ordinarily numerating them, 1, 2nd, 3rd, so there is a kind of ordered path throughout the exam. Well, you may see that somebody in the room is lying to the left, somebody is lying to the right, somebody falls asleep, somebody takes notes, but all the people are the same, and they are only swifted. Mathematicians would say there is a differential, a diffeomorphism between the configurations. So basically, since a diffeomorphism means that things are superposable maybe only by stretching, so basically they are the same. There is not a qualitative change of what we are looking at. If one of us stands up and goes out, then we are not 20, 30 or whatever, 2, but we are 1. This is a this is a sharp qualitative change of behavior. This is a bifurcation. And a loss of stability is always accompanied by bifurcation because it is a qualitative change in the behavior. But a bifurcation is not always a loss of stability, because we may have a bifurcation between 2 equally stable paths. So bifurcation is the general concept and is about qualitative behaviors, not only of mechanical machinery or structures, but also of samples of populations, of biological growth of viruses or colonies of bacteria, or of economic fluxes of financial flows. So bifurcation can be a word which applies to many fields. Of course, since we are engineers and we are used to talk about bifurcations of mechanical behavior. Well, there is also bifurcations of thermal behavior, of electrical behavior, but let us restrict our view on bifurcation of mechanical behavior. Then that it means that we may start from the very simple mathematical description of a mechanical behavior. What is the most simple way of describing a mechanical behavior? This one here. Well, this is not only mechanical. That might describe mathematical, it might describe everything, the evolution of any. We're going to phase diagrams, of course. Do you usually put signs to denote vectors?
Well, yes.
Underscores or over arrows?
Underscore is given.
Okay. Quite typically in Lagrangian mechanics of finite degrees of freedom, we have this thing here. The state variables, or the state vector, or but not only this, this is not always so. In mechanics of discrete systems, or so analytical mechanics, I say, or rigid body mechanics, it is so. Why? Because the evolution of a system, it is not only the evolution of its shape, but also of its motion. And we know that this is simply a more general way to express Newton's equation of motion, if we wish, or Lagrange's equation of motion. We are used to say that, of course, t is time, and or any evolution parameter which might be sorry, related with time, and we are used to say that when such a second, say, right-hand side does not depend explicitly on time, we talk of autonomous systems. Otherwise, this is called non-autonomous system. Okay, but those are definitions which can also be left. What do we mean? We mean that the vector field F acts on the state vector so to modify it. What is a stable? So, we are interested in motions, in evolution of shapes. What is a stability and what is a bifurcation? Sorry. What is, in this case, a bifurcation, and what is stability related to? I'm sorry, we can have let's begin. What is the solution of such a system of differential equations? It is a path, a line, say, in what we call phase space. Because this is something which dates back to the early 1900s. these are phase variables, or simply position and velocity. And we are used to say that in the simplest case, the solution is something which relates Q and Q dot. So it is a path in the phase space. So what is a bifurcation? Bifurcation is a qualitative change of behavior. So in the most interesting or most easy, best to say, way of thinking, nice path is a smooth function, a smooth curve in the phase space, such a line as I designed here, as I drawn here. Then a bifurcation is something which is related to a qualitative change of that line, or of those lines, because there might be more than one line. Solution can be not unique. Sorry. This kind of investigation is called investigation in the large or global investigation of bifurcation and or stability. But quite often we are interested in local stability, or the possibility of bifurcation in small. And usually we are related to equilibria. What is an equilibrium point? An equilibrium point is this is mathematics. Let's translate it into everyday language. What is an equilibrium point or an equilibrium state? If we were to talk to the man in the street, to people in the street, what should we say? Something is in equilibrium, or a mechanical, in particular, a mechanical apparatus is in equilibrium if, when placed, let's say placed in that configuration with the given velocity, its vector field, so the cause to alter its state, vanishes at all time. That is, the mechanical apparatus stays in that position, or in that state, which is better, because this definition is not only statical. A harmonic permanent motion is a state of equilibrium, of course, in ideal systems. So this is mathematics, but then other mathematics should, so definition. Oh, we say point, but a point is actually a configuration and its velocities. So let us always, it would be better to say state. But how can we say that such an equilibrium is stable or unstable? Then, because we may have bifurcations. So this is an equilibrium point, and from it we can see the germs of different paths. So the qualitative behavior changes, so that point of equilibrium may be what we may call, it is usually called a critical point. But we might ask, well, there are many paths originating from here. Which is stable, which is unstable, or better still, which is the correct definition of stability, following, which can follow a bifurcation? The most accepted stability of equilibrium, or but yes, stability of equilibrium is usually due to Lyapunov. Well, this is maybe the French way of transliterating it. Of course, it is a Russian name, so I wouldn't be able to write it. So the beginning of the 1900, 1917, if I'm not wrong. Which is, again, a formal translation into mathematical language of a common idea. What is stable? Okay, sorry, I have to, just 1 second. Should work. Sorry. And what is the common idea? We have learned in our basic physics courses that a small ball, a mass point, is stable in here, is unstable in here, indifferently stable here. How would we explain that? The idea of stability of a path, or in general, but of an equilibrium state in particular, or locally, let's say. Oh, why are we used, by the way, why don't we examine it or investigate global equilibria, or global bifurcation, or global stability? Because in general, it is just like when we deal with real functions of a real variable, y of x. In general, when we have a differential equation, or anyway, when we have to investigate in principle, an unknown function, we can't say globally what it happens. We might say something in a neighborhood of any of its points. So this is the principle in general. And what is the idea? It is linked to what we now call perturbations, which might be linked to the idea of a virtual displacement or a virtual change of velocity. These are all related ideas. The idea is, if I give a small disturbance to the system, what does it happen? Just imagine, we are in this room, not now, just imagine it is a very cold day, let us close everything, let us turn the heater on. The heater provides a flux of heat, which is, let's say, ideal state, uniform in time. So we reach a given temperature. Somebody opens the window. What does it happen? Heat goes out, temperature falls down. Something qualitative has changed. Temperature has changed. This is a perturbation. The system is stable if the heater provides heating and the same quantity of heat in the unit of time makes the temperature rise again until it reaches, say, 20 degrees Celsius, because it is ruled by a thermostat. What is this? What do we mean? A system is stable if following any kind of perturbation, it can react in some way, so to bring the system back to its original state. It doesn't matter how long it takes. It might be an infinite time. The mathematicians call it asymptotic stability. But this is the idea. I give a perturbation. The system has some way to go back into its original state. And this is a concept, a commonplace, a common main concept. It is something which is, yes, conceptual before being mathematical. And it is something which is maybe rooted into our intuition. And this is not linked only on statics. Just imagine we have many robotized industries, automatized industries. So there are many chains in which there are no human workmen, but robot arms doing always the same thing. I switch a thing from here to here, I switch a thing from here 10,000 zillion times. Just imagine now a workman comes just to bring new supplies and accidentally touches the robot arm. Well, the system must be designed in order to, it might deviate from the original trajectory, but it has to go back. The deviations must be kept small. And in the end, the robot arm shall retake its original trajectory. This is something, again, conceptual and intuitive. And this is what is translated into mathematics by this idea. If in the phase space, this is xe, so an equilibrium position, an equilibrium state, because it is not only a position, it's not only a configuration, it's not only a shape. It is shape and velocity, because it can be as in the case of the robot arm, a periodic motion. If I can draw two balls, maybe I should draw it, or two spheres. Remember that I draw a plane figure, but we are in a multi-dimensional virtual space. So I draw two balls. And which is the meaning of this ball? One is one of these balls or spheres has a radius of epsilon, delta of epsilon. I don't remember. I shall keep the same symbols of Angelo Luongo and all the tradition. This is epsilon, yes. And this is delta, depending on epsilon. Yes. Which is smaller than epsilon. Which is the idea? Epsilon is a measure of the disturbance. What does it mean? Of course, we are abstracting things. What does it mean, the measure of a disturbance? Well, since the state is a collection of positions and velocities, a small disturbance can be a small displacement with no velocity, or a small given velocity without changing position, without changing configuration, or a combination of the two. It can be, since we are dealing with finite dimensional vectors, we can always build a norm, a length, a generalization of Pythagoras' theorem, and so we can say that the length, the norm, the magnitude of the disturbance is small in the state space. When epsilon is small, we can have trajectories, that is, evolution paths, changes in the mechanical behavior of, sorry, not changes in the mechanical behavior, evolution of the behavior of the mechanical system, which can be this way, or this way, or this way. Sorry, that was not clear. So let's put some arrows. What does that mean mathematically, and what does that mean physically and intuitively? If I assign a disturbance and the response of the system is greater than the disturbance, grows out at even infinitively, then we are, in this case, here. I give a disturbance to the ball, and I can't stop it. That's the idea of stability. There is a path which is, according to us, is unstable. I give a disturbance, I cannot stop it. That's the idea. I open the door, I open the window, there is no control system. All the heat goes out, temperature falls to minus 20 degrees, and everybody dies. Okay, this is unstable. Or I touch the robot arm, and instead of small oscillations and recovering the same track, it starts, we say that it flutters, and in the end it smashes everywhere. This is instability, and the system is unstable. When we are, so the red path is unstable. The orange path, the orange path is stable, so we might unstable. The orange path is stable. In which sense? I might go a bit away from the equilibrium path, but I do not detach that much. How much? Oh, well, this is the meaning of delta of epsilon. I can always define what is small to me with compared to the disturbance. The most important thing is that the adjacent configuration, the new adjacent shape shall detach from the original one less than the disturbance. I give a hit, I would like that the response is less, say, than the hit. And this is the idea of the ball inside the potential well. With some slight difference, but this is more like the green one. The green one is called asymptotically stable, and it means that it doesn't matter how long it takes, but the system will return to its original position. But in any case, it is stable. Asymptotically stable. So this looks like mathematics, abstract mathematics, but actually it reflects the key ideas of what a stable path can be. So, and this applies to static problems and dynamic problems as well, because it is nowadays of key importance to define stability of dynamical systems, rotating machines, airplane wings, missiles, which are subjected to the so-called follower forces. And important infrastructures. One could never design a bridge, you have wonderful bridges here, without considering aeroelastic stability. And the principles are these. Of course, This is just an introduction, so I will not enter any detail, any particular. I will enter some details, but not so many particular details. The first bifurcations which were investigated were static bifurcations. Why? History. So maybe say the most known one is Euler's column, of course. I think everybody knows that. In every course on structural mechanics, and even I think in machine elements, one has to learn something about that, because if that were a drilling machine, then a drill point, no? Okay, I think I was able to express myself. We know that there can be a qualitative change of the behavior. So this is a bifurcation. Oh, let's try to provide some. How do we investigate the possibility of bifurcations? Lyapunov's theory, which is rather mathematical and aseptic in some way and abstract, foresees the construction of a scalar function and the necessity of investigating the quality of that scalar function. More or less, that scalar function, which is usually called Lyapunov's function, is related to the mechanical energy of the system. Just like a generalization of the ball, the massive point on a surface. But in engineering, it is usually not usual to rely on Lyapunov's function, because we usually rely on a static approach when no dynamics is present, or an energetic approach when it can be used both in statics and dynamics, but especially when dynamics is considered, an energetic approach can be useful and shall be used. I will present some pattern schemes of bifurcation, and these are, again, these are not new, but these are key to understand what a qualitative change of behavior is, and what do we mean, how we make these ideas, which are general, related to any say particular case, but with, again, general enough. So careful people, I have been telling about discrete systems, and I have quoted Euler's column. It must be something tricky, because discrete systems are defined by a finite set of variables. Euler's column is? Yes.
They ask, shouldn't the green part be always tangential to the first smaller circle?
No, not always. It must be, it might cross it, but the important is that it goes back to the origin. Usually it is preferred it keeps inside. At most tangential.
So tangential is a limit.
Yes.
So an infinite harmonic motion.
Can be that.
In case of.
Yes. But since delta it depends on epsilon, I can make delta as long as it remains inside epsilon. I can make it a bit bigger so that if the green path tends to go out, yes, it's the powerfulness of the power of this definition is right here. As long as the response is somehow confined, and I can define what a confination is. I can define the borders. Then I'm happy with that. This is the key thing. Let me just check, but it is like this. It is general. Yes, it is general. The important, I can make delta as long as it is less than epsilon, because the idea is this, is as I told, I can give a disturbance, and I shall be able to say that the disturbance is in some way, I say small, but let's say controlled. It's not an infinite source of energy. This is, of course, linked to the energy assigned from the disturbance to the system itself. It can be great in our measurement system, but it is, however, limited. And the disturbance, if the disturbance is limited, I pretend the response in terms of a path in the phase space is limited.
Well, there's only one sense of stability, the Lyapunov sense.
This is Lyapunov's, yes. And this is the one which is most accepted nowadays. And the reason is because it responds to both intuition and good mathematical treatment. So my provocation was, I talked about discrete systems, and I gave an example of Euler's column, which is continuous. So I cheated. Which is the key? The key is that this guy here, Warner Tjardos Koiter from Holland, extended in the mid-1900s the ideas of Lyapunov, which were originally for discrete Lagrangian analytical mechanical systems, extended those also to continuous systems, such as beams, plates, shells. So the key idea is this. We may investigate, we may have clear ideas by paradigmatic examples, pattern schemes, which are finite dimensional, and export the key ideas also to continuous systems. This is why we still keep on investigating very abstract systems, which are, what is the meaning of this? Just like this one. This is the basic examples which one can find almost in every textbook on stability. Oh, of course. So we have let me say, this is a rigid bar of length L. Maybe this is too thin, okay. Loaded by a given force P and constrained by a rigid hinge and a linear elastic rotation spring of stiffness K. This is a 1 degree of freedom system. Rigid body, rigid hinge, 2 degrees of simple constraint, one simple way of examining adjacent configurations. Well, what does it happen? Which are the paths in the state shape for this system? Well, if we study statics, of course, the paths are not characterized by velocities, by position and velocities, but only on positions. So x, the vector x, is not q and q dot. I hope that over dots are standards. It's not q and q dot, it's only this one, statics. Oh, what did I do? I went to the end. And in this case, q, there is only one q, small q, which is maybe an angle. Alpha phi. Let us suppose that for simplicity, P is conservative. Is it too restrictive a prescription? For some structures it is too restrictive. Bridges on Bosphorus, this is too restrictive. But for many other structures, this is not too restrictive, because civil structures which are not tall or in a high windy places, are mostly subjected to gravity, which is conservative. Okay, so conservative load may be enough. Why do we need to specify that P is conservative? Because we might find the solutions of this simple problem not only by balance of forces and torques, forces and moments, but via the principles of energy, minimizing energy. Or say, Lagrange equation with only the potential term without the kinetic term. It is exactly the same. And why do we need this? Because, as I already told you, an energetic approach is rather more general, far more general than the static one, because it works both for static applications and dynamic applications. What is an equilibrium path in this case? To have a path, one has to have, what is a path in a two-dimensional graph? A path is a line. How do we write mathematically such a line? So we have x, we have y. In principle, we should write y is a function of x. But more generally, such a line is as long as I make one step along the path, which means that I have a kind of evolution parameter, a walking parameter. I am walking by small s steps, and I'm, according to these functions, x hat, y hat, I assume a new position, x, y. Well, then, if I am to generalize this idea, then I am to be more careful. If I am to generalize these ideas, then I have to find a path parameter, which in the theory of bifurcations and stability is usually called a control parameter, which is usually a physical parameter which can be switched and modulated, just like a tuner in a radio or in a control system. I can modulate this parameter, and I expect to describe a path in my phase state. What can be, in this case, the control parameter? Have you got an idea? It can be anything. But what can it be meaningful? Usually, what are engineers doing? They have something with physical properties given, and they want to know which is the load which may cause problems, more or less. So it is reasonable to imagine red P as a control parameter. And I might ask myself, what is the path run by this bar when I vary P? Well, I have to write equations. And if you let me, I will not write everything down, but I will write something, but then I will use an algebraic manipulator. So, what is your symbol for potential energy? Capital U, okay. But I wrote here capital, say, calligraphic capital U, if you don't mind. So, this is trivially 1/2 k phi square This is it, isn't it? This is it. Do you agree? We can abstract from gravity. You know why? Because this is a phenomenon which might also occur in a horizontal plane. So gravity would be orthogonal to the direction of motion, wouldn't make no work. What else? Or is it finished here? No, you don't have to say that, Urjan. I said the load is conservative. So it derives from a potential itself. And I can't get rid of this potential because otherwise I would violate the second principle of thermodynamics. I am forgetting something in my energy balance.
Isn't it work done?
Yes. It is an active work done by a conservative force, so it is just the opposite of a potential energy. The work done by the load P on the displacement of its point of application is just the negative, or a positive work is spent by decreasing the potential energy of the load. So if I want to evaluate the potential energy of the whole system, I cannot rely only on the potential energy of the spring, but I have to rely also on the potential energy of the work, or better, on decrease of the potential energy. P times what? The displacement of the point of application of that force. And the point of application is displaced by how much? Yes. All L minus this part here. Do you agree? Is that right? Ah, sorry. Hey. Okay. Okay, this is the starting point. Then let me okay, we are talking about this system. The potential energy of the system. Okay, I didn't write phi, I wrote theta. Please forgive me. This is the potential energy. Okay, I didn't want to print the output. What does Euler-Lagrange equation tell me? That in order to find the mechanical response, the equilibrium path or the trajectory, call it as you wish, what do I have to do? I have to take the first variation of the potential energy with respect, oh, well, let's be precise once. Actually, Euler-Lagrange equation should be something like this. I think this is rather general and it does not depend on the country. But where L is kinetic energy, how do you write as usual? T, okay, capital T, minus U, or U minus T. Do you usually write U minus T? T minus U, okay, T minus U. But if we are dealing with static problems, T is either vanishing or uniform. Static means without acceleration. Doesn't mean fixed. Without acceleration. So something which moves with constant speed in one of those big ships in the Bosphorus, then it can be static at uniform speed. So we don't have such thing here. Not because we cannot write it. It's trivially zero. We have only the derivative of the potential of the Lagrangian, which is reduced to the derivative of the potential energy, of the total potential energy. And we don't have these capital Q, which are the Lagrangian components of the active forces, which do not have a potential, because everything was in the potential. So I can simply take the first derivative with respect to what? And there is only one degree of freedom. So this is the first derivative of the potential energy. And how do I have to do? What am I supposed to do to find the paths, the evolution paths of the skies? In this case, evolution is not in time, is with respect to the evolution or to the control parameter, which is the control parameter now is the load, the value of P. What am I to do? I shall equate that to 0. First derivative should be equated to 0. So this is, okay, please don't, maybe you're not accustomed to algebraic manipulators, never mind. This is just a trick. You see, find the root of this equation, and this equation is simply the first derivative, d stands for derivative, equal to 0 with respect to theta in the neighborhood of 0. Why am I looking for solutions in the neighborhood of 0? I'm reflecting the problem. I'm looking to find, is there any solution starting from my original configuration? Which is quite a Lagrangian approach. I have an initial configuration. I have some control parameter that I vary, and I'm trying to see what is the evolution, again, not necessarily with respect to time, but with respect to the control parameter. Okay, the first path is trivial, because if you equate this to 0, which is the trivial solution, theta equal to 0. But let me write it once. So I have the L, oh sorry, now it is, okay, I write it completely. In this case it is the U over the phi, or theta, pardon me, it is K phi minus P L sine phi. Did I write? Okay. And I shall equate it to 0. Well, in this case, I can solve it by hand. And I do like this, because it is quite easy to see that this is true when phi theta equals 0, whichever is the value of P. What does it mean? I can load this as much as I wish, but the bar will remain vertical. I give small, or either I give controlled perturbation of the control parameter, the position, which is an equilibrium position, of course, remains the same. So the system does not detach. Are we in such a definition? Yes. There is not even a path detaching from the equilibrium point. The system remains there. This is a stable path. And indeed, what do we expect when we load a bar by compression? It may shorten a bit, but it should remain horizontal, or better, straight. But we have this other thing. Oh, sorry, I prefer to write it like this. It is a different way of looking at it. Yes, but the fact is, there is the possibility of a bifurcation. The system may follow two paths starting from the same place. So the same point may give rise, the same shape with the same load may give rise to two different qualitative behaviors, because it's apparent that having a bar which is inclined with respect to the vertical is qualitatively different in this mechanical sense. And let's check it. So we have a second equilibrium path, which is traditionally called bifurcated. And the two paths cross at a point. That is, one of the most common bifurcations is this one. I have a control parameter, let's call it in general mu. We have a shape descriptors, a shape descriptor, a phase descriptor, a shape descriptor. And I may have one path, I might call it, fundamental. Or number one, no adjective. Number one, let me use, because of my origins, Roman letters. Or better, Latin letters, Roman numerals. And I have another one. This is what we mean by bifurcation of paths. This is also called or. This is a Latin word. The Anglo-Saxons prefer this, which actually means the same thing. We come to a node and we have different branches. And which is the point in common? Well, in this case, since the path number 1, the fundamental path, was in the neighborhood of theta equals to 0. I take the limit of this second path in the limit as theta goes to 0. And I find this. Well, I plot the two paths. Purple is the fundamental, green is bifurcated. So vertical and not vertical. So purple, vertical. Oh, well, it is just a case that the fundamental path, which represents a vertical bar, is also vertical on the y-axis, but just let's not be the same problem exists when I rotate the bar and I put it onto an horizontal plane. It remains straight along its original line, let's say like this. So this is a bifurcation by branching. There is a common point, which is, of course, the most interesting. And indeed is called critical. Why? Because if I arrive here, I don't know whether I go left, right, up, down, by switching the control parameter. How can I check about the stability of such paths, of the purple one and the green one? But I know it. How can I check stability in these simple places, in these simple patterns? The ball on a surface, or still on a line. I shall check the second derivative of its path. Or better, sorry, second derivative of the potential energy. If it is greater than 0, you remember which are the differences? You remember? About the second derivative of the energy to qualify stability of a system. We might have this thing here. Sorry. Yes, thank you, Roger. And which is the difference between them?
One greater than 0, stable.
Greater or, I didn't get it, or equal? You remember calculus?
Yes.
When does a function have a positive concavity?
Greater than 0.
Second derivative greater than 0. So it is somebody who laughs at me. Is it a stable position? Okay, then it's it. This is it. Second derivative of the potential energy is a well. What's the Turkish for it? No, a well, a potential well. Kuyu, okay. And so it is definitively stable. If somebody is angry at me, this is unstable. If somebody looks at me, indifferent or marginally stable, as it is usually said by the mathematicians. But be careful, because we are examining stability locally. So I cannot say if this line is, this straight line is long or short, because you know that when the second derivative is zero of a function or of a real function of a real variable, what does it mean? We usually have something which is called a flex. So it's not either a well nor a cusp, and it exists something called second principle of thermodynamics, or better still, Murphy's law. If something can go wrong, it will go wrong. So this is why the mathematicians call it marginally stable. Within certain margins, I might call it stable, but I don't know if, in principle, I might go left or right. So if I fall down, or if I will not be able to step up, and will remain there. So let's go back here. I might write the second derivative, which will be an expression, and I will evaluate when it is greater than, equal, or smaller than, and I might be able to plot a region of stability. So the stability threshold is that this gray line, what is below is stable, what is above is unstable. What is exactly on the gray line here is marginally stable, in the sense we said before. What are the conclusions? As long as we remain with the control parameter, the load, P. Oh, this is a, you see, this is non-dimensionalized. Remember, K is a rotation spring, so it has dimension, physical dimensions of a force times a length, because its constitutive relation is moment equal K times theta. Theta is non-dimensional, K must be force times length. So this is a pure number, this ratio, so small n is pi, is P, normal force, if you wish, and is non-dimensionalized via this value here, which is the critical value. It defines the critical point where branching can occur. The first path, so the bar remaining in its original position, is all in the shaded surface, so it is stable. As long as my control parameter is below the critical value, the bar stays vertical, or better, sorry, in its original position. Small perturbations do not affect the equilibrium of my mechanical system. The green line, which is, again, the bifurcated path, so the possibility of the bar to go left or right, and paying attention, since drawing is always ideal, I put the spring on the right, but it is immaterial if the bar goes right or left. The reaction of the spring does not depend on going right or left. the bifurcated path, or the secondary path, path number 2, which is usually called bifurcated, but I mean, the bifurcated path is stable. Why? Let us try to give a physical answer. Physical answer is even though I may assume a different shape, even though I may assume a different shape, if I give a small perturbation, a small variation of the load, say a small increase of the load, what does it happen? I am at a certain value P. Let us suppose I give a small perturbation, an epsilon. In this case, epsilon means I add or I subtract a small quantity delta P. Let us suppose I add a small quantity. What does it happen? Balance of forces, and this is the constraint reaction. It cannot be but this one. What does it happen? This is L cosine phi. This is, oh, sorry. L sine phi. If I increment the load, what happens? There is an increment of the outer active couple. The moment increases. So, what do I expect mechanically? The system should rotate by a quantity delta phi, delta theta. But what is there here? A spring. What does the spring do? Whenever I tend to rotate, its extremities with respect to each other, it reacts. It reacts. And tends to stop the bar, to bring it back to its position. So even each one of these positions is stable. This is the physical meaning of this path green being in the stable region. Even if it is a bifurcated path, even if it is another path, as I told you at the beginning, bifurcation doesn't always mean loss of stability. I may have two paths, but both might be stable. What does it happen? When I am along the fundamental path, along the bar staying straight, above the stability threshold, so if I bring the system here, in some artificial way, this is an equilibrium position, but it is unstable. What does it mean? Small perturbations of the load will immediately bring it on the other path. on the green one. It will go far away. So we are here in the red path. It goes away. Qualitatively, abruptly changes its quality. So in that case, we have a problem. Why? Because nobody assures us that, in this plot, the bifurcated path is very flat. So if I start from this point here and give a small perturbation, the system wishes to recover an equilibrium position, and to intersecate the green line, it must go many thetas away, which means in actual engineering systems, linearity is lost, plasticity is attained, maybe fracture. So, studying critical points is fundamental. But do critical points exist? Because this is theory, this is pure mathematics. Do critical points exist? Have a look here. I wrote perfect systems. In which sense did I deal with a perfect system? This thing here is a perfect system in the sense that hinges are smooth. So there is no friction, there is no dissipation. The spring is perfectly ideally linear. The bar is perfectly along a line, straight, vertical, horizontal, along a given line, and the load is exactly coaxial on the same line. Do we believe that in our engineering actual activities we are able to attain all these things? Perfectly centered load, perfectly homogeneous material, perfectly linear elastic response, perfectly smooth hinges. We have grown up, and we know that there is no such thing as a Santa Claus. No, there is. There are presents in season's greetings. Well, I'm used to talk about Western customs, but I think Western habits. But I think that you also have some not Christmas, season's greetings. Sorry, I don't want to. So we say, be careful, we don't have perfect systems. We have, in general, imperfect systems. What do we mean by imperfect systems? Systems that are related in some way to the fact that there are uncertainties. And the most trivial way to model these uncertainties in such basic pattern is this one. So imperfection might be introduced by an initial deviation from the ideal situation. Which is the ideal situation? Let us keep something easy, smooth constraint, perfectly linear elastic response. So the only thing is the bar is not perfectly straight, or, which is the same, the load is not perfectly on the same line of the bar. Well, in this case, nothing particularly, it is not so difficult to write things, because how do I examine the problem? I shall write the potential energy, which is the difference. I will only, instead of writing the first, I shall write this thing here. And analogously for the work done by the external forces. So I will not write everything down, but this is the thing, you see? Theta minus theta 0 and 1 minus cosine theta minus 1 minus cosine theta 0. Trivial. Or trivial. Easy. Sorry, not even. If imperfections are small, so theta 0 or phi 0 is not that far from 0, then cosine theta 0 can be expanded into series, into power series, around 0. Maybe we stop at the first order. This is what I've done here. So this is the modified expressions, the modified expression of the potential energy for an imperfect real system, always idealized, modeled, but let's do the same. First derivative, what it is for, to find the equilibrium paths. Let us equate it to 0. Sorry. The presence of this term here, theta 0, maybe just have a look. Compare it with now, with this. You see? There was the possibility of having one solution in terms of phi for all p, and one solution for p in terms of phi. But now the equation is like this. There is something like k phi, something which is k phi 0, and then pl sine phi. And I'm not interested in signs, or maybe it is minus minus, but it's not important. You see, there is no possibility of saying the same thing is above. There is only one path. So, bifurcation does not exist. We are talking nonsense. It is useless to study stability theory or bifurcation theory. Well, let's check the stability of this new path. And we plot a series of these paths, keeping phi 0 or theta 0 as a parameter. So I plot a series of paths depending on the values of theta 0. Well, maybe I have to. what does it happen? This line, vertical line, is not only the y-axis, or say the control parameter. It is also the fundamental path of the perfect system. The green line is also always the bifurcated path of the perfect system. Gray line is the stability threshold. Gray surface is the stability the stability region, the stability stable region. We have a collections of paths. So this is, I hate this, but I don't know if I can. No. Okay, it is not so clear. I should. Forgive me. Okay, maybe I can do this. Okay. Now it is maybe more clear. And never mind if. Oh no, you can read it. Okay. Have a look. Let us begin with a small imperfection. With this pi over 20, which means 9 degrees. If I modulate the control parameter, so I start loading the system from 0, the system, remember, the system is not perfectly vertical. It is slightly inclined by 9 degrees, pi over 20. This is the imperfection. This is the initial imperfection. The system will not follow the perfect path, which is vertical, because it did not start from vertical. It was not ideal. It was imperfect. In some way, we took reality into account. So we follow this path. Well, it is rather vertical, so it resembles.
It's not 9 degrees.
Sorry?
It's not 9 degrees.
No. The imperfection is 9 degrees. This amount here is 9 degrees.
Oh, I see, okay.
This curve, no, you're right. It's pi over 100. Yes, it is 1.8 degrees. Yes, you're right. Sorry, I had read it the wrong way. So very small deviation. And have a look. It is almost vertical, so it resembles the fundamental path, but there is no bifurcation. When? Well, there's no need to evaluate the critical point then. But real systems do not even reach the critical point. Well before the critical point, the behavior changes, or well, let's say, the path changes. Well, it's a function. Why do I care about the function? It might grow, it might go down. Well, but this function represents a physical behavior. It is almost vertical in the beginning. It becomes almost horizontal. What does it mean? This is more or less. We are representing control parameter now general control parameter I had called mu, now it is P. I'm running out of time, I'll take only some minutes. P against the angle phi or theta. Active force, change of shape. Do I remember something? Active force, change of shape.
Drop down on the curve.
Have you ever seen something like this? Traction, pure traction of a material. So, and what is the meaning, the physical meaning of this thing here? Stiffness of the material, elastic modulus, stiffness of the material. Is it the same here? Oh yes, it is the same. Because it is directly linked to the first derivative of the total potential energy. And what is the first derivative? It is directly linked to the stiffness of the system and how the stiffness is affected by the geometric change of shape and the presence of the load. So it is the slope of the path has a perfect and clear physical meaning. It is straightly linked to the global stiffness of the system, say global. Okay, let's say the global system of the stiffness of the system, which takes into account not only the elastic stiffness, so the intrinsic properties of the system, but also the fact that since the configuration, the shape has changed, lever arms have changed. Moments are different and they affect differently the global behavior of the system. So, and as a matter of fact, this is general, not only for the system. And as a matter of fact, this is usually called elastic stiffness. And this is called, or elastic contribution, and this is called geometric contribution. Because it has to do only, the load is given. It might be controlled, but it is given. But since the shape changes, the same load may have different lever arms and affect differently the equilibrium. So, let's go back here. Here we have great stiffness. Next to infinity. But in the ideal system, the bar was rigid. And if we load it along its direction, it has infinite stiffness. So if we do not detach that much from the ideal bar, stiffness is almost infinite. But as long as we run the path, we modulate the load, we increase it, and we go towards reaching the critical load, that's what it happens. Stiffness suddenly goes down. What do we expect then if the stiffness suddenly goes down? We expect in real world systems that your loading capacity is almost reduced to zero. That means that quite likely you're going to destroy your apparatus. Have you ever drilled something with a drilling machine with a very slender point, with a very slender yes, well, but the drill is the whole apparatus. Then you change the punta. Okay, never mind. I think you got it. If you reach the critical load, or if you arrive next to the critical load, you see the beam which drills the hole bends. If you're able to go to slow the motion or to unload it, then it will regain its original position. Otherwise, its stiffness is gone. And it's so low that even a steel element can be broken. I have broken more than one because I didn't study this. And this phenomenon is stressed and is worse when the imperfection grows. You see, passing from blue to purple line, so augmenting the imperfection, we have that the passage, we don't have any critical point, we don't have deramation, we don't have branching, but we see a dramatic fall of the stiffness of the system. And this is always for the greater the imperfection, the lesser the load in the vicinity of which we see a dramatic change in behavior. And this is not, it does not depend whether the imperfection is positive or negative. You see, we might have a blue line or the corresponding perfectly symmetric yellow line, and so on and so on. Mathematically, next to this blue line, there is this other blue line. They are part of the same function. It is a function divided in two. We know there are functions which have two different laws for different domains of definition. This we have learned in calculus. Well, we have two different laws. But if we start loading the structure from zero, this is the natural path. This is unnatural, which does not mean that it is not attained. But we have to bring the system there by constraining it. Have a look. All these paths, natural paths, are stable. So in principle, we shouldn't worry about that. But this is a very simple scheme. I considered only one cause of imperfection. I considered only one control parameter. So it is, it is an ideal imperfection. What do we expect in real systems? Things might not be so pleasant. Only 5 minutes and I'll be finished. We might think the world is nice, because in any case, imperfect paths can stay in stable regions, but unfortunately, there are other very simple examples of mechanical systems. This is a very simple example, but, oh, by the way, that is a discrete approximation of a flexible beam. because any flexible beam can be discretized like this. This is called a Henke bar chain.
The stiffness of the springs goes to infinity, it's normal.
By all these are rigid bars. It's very short, so you may simulate with discrete systems the fact that a beam is flexible. And if, of course, if those rings do not exist, you have a motorcycle chain or a bicycle chain. So a mechanism, or in any case, I mean, this is an ideal mechanical system which can be used to describe actual continuous beams or continuous structural elements. Now I will not so this time I will not put it vertical. This is another very simple system. What did I change? Oh, sorry, this is a rigid bar. Sorry. This is a rigid bar. What did I change? I didn't change geometry. There is a linear elastic element, but it is not an element in rotation, it is an element in translation, or say, not in relative rotation, but in relative displacement of its extremities. And it is not at the basis, but at the other, say, at the free end. Okay, in principle, am I able to write? Well, it is always a system with 1 degree of freedom. Its shapes are described by a single variable phi, again, or theta. How do I write the potential energy due to the strain of the spring? 1 over 2 k, and the displacement is extreme, which is of the extremity, which is directly linked to L and sine phi or cosine phi. So, and the expression of the work done by the load is exactly the same. So I will not enter into the details. I will simply these are potential energy. Okay. Believe it or not, this is its potential energy. You see, this is the displacement of the L sine phi or sine theta. And this is the same, the work done by N or P. Okay? Second derivative, first derivative are equal to 0. Oh, there are 2 branches. One is theta equals 0, so the bar remains in its initial configuration. Or there is another branch. Okay, let's see how these branches are like. Now, purple is the fundamental. So theta remains 0 for all values of P, of the load. Or the load has this low here, KL cosine theta, for any theta. Okay. There is a branch. There is there is a branching, there is a critical point. It is more or less the same as before. By the way, these are usually called pitchfork bifurcation because it seems like a fork with 3 teeth. And pitch stands modulated fork. Pitch. So it doesn't seem anything special. Let's evaluate its stability. Okay, there are some functions. Never mind. The quality of the stability is dramatically different.
Could you show potential energy again?
Yes, of course.
I'm confused a little bit. When you write in paint, I will work 1/2K times P squared by in the...
No, it's not fine. You should evaluate this thing here.
Okay. Okay.
Now it is a spring in elongation, so you should evaluate this quantity here, which is L sine phi to the square. Okay? No, your questions are always welcome. No, never mind. The gray shaded region, which is the region where the system is stable, is dramatically different. Is well below the bifurcated path. What does it mean? My system is stable only when the load is in the neighborhood of the so within the limits of the critical point. Everything is again non-dimensional, so I can only plot numbers without taking care of specifying metrical units. So this quantity is non-dimensional because now K is an elongation spring, so force over a length. So KL has the same dimension of force, so this is a non-dimensional expression. And indeed, the critical point is always 1 because it has been rescaled. So the critical point, where is it, is KL, because in the neighborhood of theta equals 0, the two branches in the neighborhood of theta equals 0 meet at KL. You see, for theta tends, when theta tends to 0, this branch equals KL. So the critical point is KL. If I non-dimensionalize, critical point is 1, no, N over KL. As far as I am below the critical point, the fundamental path is stable. All the rest is unstable. And when I deal with imperfections, there is nothing special. I simply say that it is not perfectly horizontal, but that there is a slight deviation. Small imperfections. Again, this is the first derivative, so which has to be equated to 0, and there is no bifurcation again. But let me do the same thing as above. Not only the stability region is below the bifurcated path. But have a look at the real, say, ideal imperfect paths. They begin almost vertically, so stiffness is almost infinite. If the deviation from perfect structure is negligible, I charge along the, more or less along the rigid bar, so stiffness is almost infinite. But then you see how there is an incredible change in the behavior. Stiffness, have a look at, stiffness decreases, okay, decreases in magnitude, but the curve is monotonic. It is a kind of hardening. You see, it decreases dramatically, and then it slowly begins to grow again. Like here, it suddenly decreases, then a bit grows again, like a hardening phenomenon. It is not the material which behaves like this. It is the effect of the geometry, of the change in the geometry. As the experts say, it's not the elastic stiffness, it is the geometric contribution of the stiffness which changes everything. So this was that system. Have a look, this system. There is a dramatic change here, exactly where the path meets the threshold of stability. Stiffness goes to 0. And then it decreases. Stiffness goes to 0 and then decreases. What do we expect to have there? Crisis. At least crisis. Maybe, I don't know if it is a crisis for plasticization or real fracture. But I expect my mechanism or my structure not to be reliable anymore. And what is worse, stiffness becomes negative. That is exactly in a load, in a traction, prova di trazione, a tension test, a traction test. With the same load level, I might have negative stiffness means that deformation increases with the same load level, which is actually crisis. And this behavior does not depend on the sign of the imperfection. It is the same on the left and on the right, so positive and negative imperfection. And I don't care, even if I bring the system in these non-natural paths. Have a look. Stiffness is always negative, and actually they lie on the white part, on the white region, that is the unstable region. These peaks here are usually called ultimate loads. And I will show you only the graph, only 2 graphs more. There are even worse systems. Of course, they are idealizations, but there are actual physical systems that behave like this. Like the first one, I already told you that the first instance was that of could simulate a bar in bending. This, just try to exert your fantasy. What can this simulate? Urjan, you're not allowed to tell. You do know me too much. A bar with a tendon. There are many in bridges. A sustaining tendon. Well, it is a bit more complicated to evaluate the potential energy because one has to do some trigonometry to evaluate the elongation of the spring. But in principle, it is not difficult. The procedure is all the same. It is just a little bit more complicated. But so, trust me, I did these calculations, and somebody else did them much before me, and they are exact. So. Believe me, this is its potential energy. This is its the first derivative of the potential energy. Have a look. There is always a stiffness term depending on K, and there's always a geometrical term depending on linearly proportional to the load, but depending on the geometry, on the change in geometry. So there is always elastic stiffness, elastic contribution, and geometric contribution. There is bifurcation. There are two paths. This is the critical point. These are the two paths. Always purple one, green one. Again, perfect path. Bar is loaded on link compression. Force runs throughout the rigid bar and disappears in the universe. Nothing has changed. Bifurcated path, there is the possibility of changing. And what is the first thing which appears, which is clearly appearing? The graph is no more symmetrical. Because now this disposition, this geometrical disposition, is not symmetrical anymore. Ask yourself why. You're perfectly capable of answering that question. But the fact is, so it is not immaterial whether the new path is on the left or on the right, or up or down, okay, on one side or on another. Here it is stability threshold, and usually green region is stability, where the system is stable. White region is where it is unstable, boundary of stability. Have a look. Qualitatively, there is one part, okay, the fundamental path is always stable. One part of the bifurcated path is stable, the other part is unstable. Who can assure me which is where the system will go? But what is much worse, when I introduce imperfections, small imperfections, of course. Yeah, I know it can be made simpler, but I like running one by one. What does it happen? On one side, the system behaves like the first one. Oh, bifurcation disappears. But on one side, if the imperfection is on one side, who assures us that it is on that side? The system is hardening in the general meaning we have discussed. But on the other side, it is softening, and it has limit loads, after which the stiffness is negative. These are systems which are called very sensitive to imperfections. What do we mean? We are not able to characterize whether an imperfection is positive or negative, because this is an ideal imperfection. We have said we are able to describe it only with one parameter. Who said this? Who can assure this? And who can assure us that we are on the left side, the stable branch, or on the right side? So either we keep a very low level of load. It's just like in fatigue. If we want to have an element which lasts forever, we shall load it by such a very small load, so to be in some way reassured that we are well below the limit of fatigue by 10 zillion cycles. But can we design something like this? Oh yes, we can, but then it would be a loss of a big amount of money. So, yes, of course.
Room line, there's no point whose slope is 0.
Because it is the ideal bifurcation point, the ideal bifurcation path. Remember, vertical is ideal, perfect, fundamental. Green is ideal, perfect, bifurcated. All the other lines are affected by imperfections. So, vertical and green meet at the bifurcation point. There is a bifurcation in ideal systems. Whenever I have a non-ideal system, so when I don't start from 0, 0, an ideal system starts from 0, 0. Whenever I start 0 load but some imperfection, so slightly on the left, slightly on the right, I don't see any branching anymore. There is no critical point. But I can have either a hardening or a softening behavior, and statistically I'm not able to say whether I'll move in the hardening branch or in a softening branch. So even when talking about static bifurcation, there is nothing dynamic here. And one of the most important, some of the most important bifurcation cases are those of dynamics, flattering and galloping. Flattering, what is flattering? Have you ever watered your garden? Do you know what I mean? Can you translate that for me? There's somebody also behind you. if you open the water above a certain pressure, then your soft hose will become doing like this. It starts from equilibrium, which is static. It goes on to another equilibrium, which is dynamic, because it oscillates harmonically. No problem. But if you keep on growing the pressure of water, amplitude might become dangerous. But there is still another one, which is still more dangerous, which is what is called galloping. And it's, this will be the last, then we will, which is typical of aeroelastic structures, and even bridges then. How do you call fence, when you, police scene crime, those thin stripes which are put by workmen to delimit, yeah? Please help me if there is a translation. Okay? Just imagine there's some wind. Do you see them in equilibrium without any movement? Blow on them. Just imagine there's some wind. What happens? You have a string in our horizontal position, wind comes from orthogonally, and you start, at a certain time, you start seeing them doing like this. It oscillates in its transverse direction. It is a bifurcation. And of course, if it is something which happens on such a tiny thing, just imagine an airplane wing or a bridge deck. What is the phenomenon? Wind comes, there is circulation of fluid around the shape of the, say, the beam or the nastro, thread, ribbon, yes, nastro, ribbon, thank you, or the ribbon, and if the ribbon is deformable enough, since the pressure is never uniform, it will bend a bit, it will twist a bit, then it creates like an airplane wing. There is an angle of attack, circulation is not uniform, and you have lift and drag. So it tends to go up and back. So you see the ribbon which is slightly bent, but begins, after a certain level of velocity, it might begin to do like this. It begins to oscillate in the transversal plane. If these oscillations are damped, no problem. But I think you might have seen some of those ribbons which nobody has tear apart, which are torn apart, only because of the wind. Just imagine an airplane wing, or a bridge deck. That's why modern bridge engineers cannot be detached from mechanical engineers and aeronautical engineers, and from control engineers and control theory engineers. I have talked too much. Let's cut it here for the while. Yes, an hour and a half, and I'll try to be very short in the second part. I beg your pardon. Now, as you know, when I talk about subjects which are interesting, at least to me, many thanks for your patience.